Pierre Colmez from CNRS, University of Sopot, and he's a recipient of the Science Award, the Frontiers of Science Award, and he will talk about the periodic local Langlands correspondence. Let's welcome.
Okay, so, well, I'm quite happy to be here, so thank you for the invitation. So I'm going to speak about joint work that we did with over the years with Gabriel Dospinescu and Niziol. And so we have a series of papers, and so one that got the award is the first in the series. So I will focus more on this one, but I will also explain things about the general strategy. And so before speaking of our work, I'm going to review what was known about the p-adic local Langlands correspondence for GL2QP and why we want to do what we do. Yes, so first I need some notations. So L is going to be a finite extension of QP, which will be the field of coefficients for all the representation of the groups that we are going to consider. And then G is going to be the group GL2 of QP. And then we have the Galois group of QP, absolute Galois group of QP, and inside it we have the Veil group, where we discretize Frobenius. So by local class field theory, we have a, we have a identification between the continuous character of the Veil group and the continuous character of QP star. And under this identification, this atomic character here, cyclotomic character, corresponds to the characters that sends X to X norm of X. Okay? So what are the main players? So on the one side, you have representation of G. So these representations that you are going to consider are unitary, admissible finite length. So what does unitary means? It means that it is a representation on a Banach space, L Banach space. And unitary means that there is a lattice. Well, no. Okay, there is a lattice pi naught, which is complete for the p-adic topology, so which is going to define the topology on pi, which is invariant under G. Okay, so that's what unitary means. So there is an invariant lattice. Admissible means that if you look mod p to the n, so the representation of G is smooth, locally constant. And admissible means that if you look at any open subgroup, the space of fixed vectors is finite dimensional. So it's a classical definition in a complex world. And finite length here means it is finite length as a topological module. So as a topological representation of G. Okay, and so that's one side of the story. The other side of the story are the representation of the absolute output of QP. So when did I start exactly? Like 47? Are you sure? I don't really believe you. So, okay, so we have the p-adic local Langlands correspondence is given by a functor that sends a representation of GL2 of QP to a Galois representation. But here there is nothing about the dimension of the representation. As the correspondence itself, so it's something that starts from a two-dimensional representation. The 2 here is for dimension 2. And that produce for you one representation, so a unitary representation of GL2 of QP with the following properties. So if you apply the functor, previous functor to this representation, you get a V back. And then this functor kills all objects of finite dimension. So you insist that there is no finite dimensional subobject, and it's maximal for these two properties, okay? And so if you do that, then it gives you a well-defined correspondence. And so the definition of the functor is not difficult. So this if you take the dual of representation pi, then it's naturally a module of over the measures over QP. And so if you want to turn this into a ring, you have to put some a degrowth condition at infinity, so that it tends to 0 at infinity. Otherwise, you cannot multiply the measures on QP. And there is an action, I mean, you can turn the action of P001 into an operator that you call phi. And you can also take the action of sigma A, where A is in CP star. And so you get also an action of ZP star. And so this is exactly what is called the phi gamma module. And then there is a recipe by Fontaine that turns the phi gamma module into a Galois representation. So the recipe is you take your phi gamma module, you transfer by one of these Fontaine rings, and you take the invariant under Frobenius, and then you get a Galois representation. So this functor is easy to construct. What is hard is to prove that if you start from a representation of GL2 of QP, what you get here is finite dimensional. So that's the hard part of the, I mean, one of the hard part. And the second hard part is to prove that any two-dimensional representation is hit by the functor. So that's the two main difficulties. So this correspondence has a lot of nice properties. So the first one is compatible with class field theory in the sense that if you look at the central character, so the center of GL2 of 2P acts through a character, then it corresponds to the determinant of the representation twisted by the cyclotomic character. The second thing is that it gives you a bijection. So this the correspondent gives you a bijection between irreducible representation of the absolute Galois group, two-dimensional, and what we call supersingular pi. So supersingular means that you have irreducible representation, which are not Jordan-Holder constituent of induced representation of a character of the Borel. So induced representation of a character of the Borel are called principal series representations, and supersingular ones are the other ones. If your representation, Galois representation, is not irreducible, so its semi-simplification is a direct sum of two characters, then the representation you get by the correspondence is also not irreducible, and the Jordan-Holder constituent are exactly the Jordan-Holder of two induced representation of explicit characters of the Borel that are made from the two characters using local class field theory. And the last thing about Jordan-Holder constituent is that any absolutely irreducible representation of GL2 of QP appears as the Jordan-Holder constituent in one of these pi of V. So you cover all possible representation of GL2 of QP in this way. Okay, and then there is also a relationship to classical local Langlands correspondence, which is the following. So inside this pi of V, you can look at special vectors. So in particular, you can look at vectors which are locally analytic, meaning that the action of GL2 of QP is locally analytic on your vector. You can look at the vectors which are locally algebraic. So the action is given by polynomials in the entries of the matrix. So the theorem is that you have locally algebraic vectors if and only if your Galois representation is what is called de Rham with odd shaped weights which are distinct. So the RAM is a notion that was defined by Fontaine to capture representations that come from algebraic geometry, and I don't want to get into the definition. And the relationship is that these locally algebraic vectors, they are given, so if you are the RAM, then there is a space called dpst of V, which is a representation of the veil group, or in fact the veil Dulling group. And LL is the classical local Langlands correspondence. So it's a representation of GL2 of QP, which is smooth. So the action of GL2 of QP is locally constant. So this comes from the classical local Langlands correspondence. So it's a locally constant representation of GL2 of QP. And this is an algebraic representation. So this sim B minus I minus 1 is just the symmetric power of the standard representation of GL2 of QP on QP square. So, there is, and then you have to twist by the determinant. Okay? And then there is also a recipe to recover the classical local Langlands correspondence in case the two, it's still the RAM, but the Hochschild weights are the same. So it's not true that they are locally algebraic vectors, so you can not use the local algebraic vectors, but there is still a recipe. And finally, there is, no, not finally, there is also some other properties, but there is a compatibility with reduction mod P. So there is also a local Langlands correspondence modulo P. And what this says is that if you mod out, if you choose lattices on both sides and mod out, then they are going to correspond by the correspondence. And so if you look at the semi-simple version of it, it tells you the following. It tells you that there is a natural bijection between the mod P representation of GL2 of QP and the two-dimensional semi-simple representation mod P of the absolute Galois group of Q. So what are these blocks? The blocks, so in a category, two elements are in the same block if you can find a non-trivial extension, I mean a chain of non-trivial extension between your two elements. So, well, okay. Yes, showcase here. So if you can find non-trivial extension like this, sigma 1, sigma 2, etc. So sigma n. And so each of these extensions are non-trivial. And so sigma 1 and sigma n are said to be in the same block. Okay, so you have a bijection between blocks and a representation, representation of GL2 of QP and semi-stable representation of the Galois group. And finally, there is a compatibility with the global correspondence. And the statement is that this pi of V that I described, they appear in the cohomology of towers of modular curves. There. Yeah. So, and then, so one application that we have, and which will show up a little bit later in the talk, is that you can recover a representation pi. So if you start from representation pi, you can recover this representation from its locally analytic vectors. So I wrote something about the dual, but if you translate, if you dualize back, what it says is that if you start from a pi and you take the locally analytic vectors, and then you take what is called the universal completion, then you get back your pi again. And this is a very natural statement. And so it's a question of Emerton whether it is true for any G. But the only proof that we know is going through this correspondence, explicit correspondence for GL2 of QP. So it really uses Galois representations, and there is no direct proof of this statement for GL2 of QP. Okay, so let me give you some history of these results, because I mean, there was a lot of work in it. So probably it started with Bardel and Livney in the early 1990s, which classified partially the mod P representation of GL2 of F for any finite extension F of QP. And this was completed by Breuil. So what they did is that they had things that they could prove were irreducible, and there was some things that were called super singular, which they could not classify. And so Breuil could do it, but only for GL2 of QP. And then there were some later work by Breuil and Pascunas trying to do this for GL2 of F. But for GL2 of F, the situation is a complete mess, and we still don't understand what should be the correct statement. Okay, and then at the same time, I mean, a little bit later, Schneider and Teichbaum wrote quite a few papers on the foundations of unitary representation of p-adic groups. So the ones that appeared on the side of GL2 of QP. So they isolated the notion of admissibility. So they were mimicking things that were done in a complex world, but here, I mean, you asked admissibility mod P, so it was not totally obvious. What they did more was to study the locally analytic and locally algebraic vectors. And their main theorem was to prove that they were always locally analytic vectors, and that in fact the locally analytic vectors are dense in the representation. So that's probably their main theorem. And then, so I mean, in representation theory, there is a basic tool which is a Schur lemma. Usually, if you have a irreducible representation, the endomorphisms are supposed to be scalars. And so nobody could prove it. And it was proven by Dospinescu in 2012, but it was building on a very, very big work by Ardakov and Watzley. Then at the same time, Breuil started to work on this problem after the proof of the tiny conjecture following. So the tiny conjecture was proved in full generality in 1999 by Breuil, Diamond, Conrad, and Taylor, but it was based on the work of Wiles that proved Fermat's last theorem. And so by looking at the computations that appeared in the proof, he realized that some computation that they were doing on the Galois side had counterparts on the GL2 of QP side that were much simpler. And so he started to wonder whether there would not be the p-adic stories that would explain this. And so, his idea was that, okay, so if you start from a Doram representation, as I told you, attached to a Doram representation, there is a naturally a representation of the Veil-Delin group. Attached to a representation of the Veil-Delin group, there is naturally a representation of GL2 of QP, or GLN of F in general, given by the classical local Langlands correspondence. Okay? But the Doram representation are classified by this Veil-Delin representation plus some extra data, which is a filtration on this representation. And so the question was where could you find this extra data? And so Breuil's idea was that it could be found inside by looking at possible completions of the representation coming from local Langlands correspondence, classical local Langlands correspondence. So this filtration should correspond to some analytic data, some topological data on this classical Langlands correspondence. And he made a very precise conjecture in 2 dimensions for the simplest case of the ramp representation, namely the crystalline and semi-stable. Around the same period, Emerton introduced what is called completed cohomology. So, I mean, for GL2, you just look at the tower of modular curves, you look at the étale cohomology of this tower and just complete the inductive limit. So that's what's called completed cohomology. And you can do, so this is a story for GL2 of Q. You can do the same story for any reductive group. And he stated a very influential conjecture on local global compatibility. So this completed cohomology is supposed to be some global object. And he stated that inside the completed cohomology, you could find these representations that Breuil was claiming should exist, and he gave a very concrete statement. And so the next step was the proof of this Breuil's conjecture in the year 2004-2005. And so it was done in 3 steps. So I proved the case of semi-stable representations. And then it was, so the proof was adapted to the crystalline case by Berger and Breuil. And then I introduced the concept of triangular representation that interpolates all these representations in a big family that you can that corresponds to so if you know about p-adic modular forms, in the p-adic world there is something called the Colmez curve, eigencurve, which is you can actually construct using completed cohomology, and so triangular representation corresponds exactly to the things you find in this Colmez curve. And then in the last 4 years, next 4 years, I defined this functor V and pi and a study of locally analytic and algebraic vectors. And then Dospinescu proved the existence of infinitesimal characters, and so which gave a nicer proof for the characterization of algebraic vectors. And this has application to Fontaine-Mazur conjecture. So from the description of local algebraic vectors that I mentioned, they were Tissin and Emerton proved most cases of the Fontaine-Mazur conjecture for GL2 of Q. And this was completed by Lou et Pan in 2019. And in 2008, Emerton proved the full local global compatibility, which he had conjectured. So, no, it's not the full. He proved in most cases its local global compatibility. And this has been revisited by these 6 authors and by myself, Sean Wen Wang, and by Lou et Pan. Then Pascunas made a very, very important contribution. So, as I mentioned, so I was starting with representation of GL2 of QP, which are finite lengths as topological G module. But actually, for the construction of the functor V to work, you need the representation mod P to be a finite length. And what Pascunas proved is that if you start from something which is irreducible in characteristic 0, then mod P, it is finite length, which was absolutely not obvious to start with. And he also proved a very important statement where he describes the whole space of representation of GL2 of QP, for which the Jordan-Hölder constituent mod P fall in a given block. And he describes this purely in Galois terms. So, a posteriori, this can be seen as some kind of local categorification, meaning that you can describe a representation of GL2 of QP as some kind of coherent module on the space of Galois representation. So finally, in 2014, with Dospinescu and Pașcunas, we treated the remaining cases that were not done before. And also, we proved the compatibility with class field theory, which was not done before, in fact. And finally, we have this amazing announcement by Dotto and Mertonji that you can actually categorify the entire correspondence. So what does it mean? So Pașcunas was working one residual representation at the time. And so, so the space of deformation of one residual representation is basically most of the time some kind of unit ball. And so what Mertonji did was to put all this unit ball in some algebraic object, which is a stack of phi gamma modules. So phi gamma modules correspond to Galois representation. So the points are the same, but you have more families of phi gamma modules than you have of Galois representation. So if you look at the entire family of phi gamma module, it is parameterized by some algebraic object which is almost connected. Whereas if you look at Galois representation, you have one for each residual. I mean, you have a connected component for each residual representation. And so what they prove is that the finitely presented representation of GL2 of QP, which are finitely presented modulo P to the n for all n, they correspond to coherent modules on their stack, Mertonji stack. So, but it's still not written. So, as you can imagine, we would like to have the same kind of description for other groups. And the bad news is that there is no single other group which is not directly related to GL2 of QP, like SL2 of QP or PGL2 of QP, for which we know what the answer should be. And so there are some different attempts to generalize what we could do for GL2 of QP. So there is this attempt by the sixth author, which say, well, okay, so we have this local global compatibility for GL2 of QP. So one way to go around should be to look at completed cohomology of towers of Shimura curves and see what we find there, and just basically define pi of v by what we find in completed cohomology. But this is not very satisfactory because your v is a local representation, and then you have to put it inside a global representation. And so there is already a lot of choices there. And then you have to choose Shimura variety. There is other choices there, and so on. And so in the end, you get potentially many pi of these, and you don't know that they are all the same. So some people conjecture they are all the same, and some people like me have a tendency to think that this is not true. So, but so we will see who's right. Now, there are also attempts by Breuil and many of his collaborators and former students. So, for example, Yi Wending, Yongchuan Hu, Florian Herzig, Hellman, Schrenn, and probably I forgot many of them. So, what they do, they construct either mod P or using local identity vectors some parts of what the representation pi of v should be. So you start from pieces that you know should be there, and you try to find an extension between these pieces, and you want them to be big enough to actually encode V itself. Okay, so they are successful in doing that, but still and also yes, and so one reality check is to check that what you construct can be seen in completed cohomology. So you need to, otherwise it will be useless in fact. And so they can do it in many cases, and this has very nice applications to modularity problems. So, and then finally there is this categorification by Merton G. Hellman. So the statement I told you for GL2 of QP, they have a completely general conjectural picture for GLN of F, or F is an extension of QP and NN. There. So, and so our approach is different. So we try to mimic what was done for the classical local Langlands correspondence. And so it is known by the work of many people that I will recall a little bit later to appear in the cohomology of the Drinfeld tower. And so the classical correspondence uses the L-adic cohomology for L not P. And so our plan is to use P-adic for L equal P, for L equal P. So I will explain that it is not a very bright idea. I think that anybody working in the field would have this idea, but I will tell you why nobody did it before. So, but first I have to tell you what Drinfeld tower is. So you start from Drinfeld upper half plane. So you take P1 and you remove all the points defined over QP. So you get an analytic curve defined over QP, and which comes with an action of GL2 of QP by Möbius transformation. Then Drinfeld also defined a tower of étale G equivariant coverings. So this was done by interpreting this upper half plane as a moduli space for p-divisible group. And then this tower was constructed by just adding some level structure to these p-divisible groups. And Scholze and Weinstein actually proved that this tower is cofinal in the system of all étale G equivalent coverings. So this these coverings are defined over Q bar, QP breve, which is just the p-adic completion of the maximal unramified extension of QP. And there is an action of W of QP, but not of Galois, because I mean, there are infinitely many connected components, and this, I mean, Frobenius permutates these components in a non-continuous way for Galois, so you cannot. So, for example, I mean, in the first stage, the first level is just to take the Drinfeld upper half plane and you multiply it by Z, so you take the product with Z. And one thing that is known about this tower is that if you look at the Dospinescu component, it's naturally QP star. And at a lower level, then it's given by the units in the quaternion algebra. So D is the quaternion algebra, OD is the ring of integer, and pi D is the uniformizer. So the automorphism group of the whole tower is GH. And so as you see, this first layer is infinite, but then all of these are just finite coverings, étale coverings. Okay, and so now on this space, you have the action of these three groups, G, GH, and the Y group. And so it's going to act on any cohomology theory. So by definition, the cohomology of the tower at infinity is just the inductive limit at finite level. Yeah. So for example, so the result I was mentioning before is that for L equal P, if you look at the étal or pro-étal cohomology of this tower with coefficient in QL, then you recover it has the following decomposition. So the sum is over all the two-dimensional Veil-Delin representation. And so the cosocle is just the reducible. I mean, it's not necessarily irreducible, so you just take the quotient. In general, it is irreducible, so the cosocle is equal to M. And so what are these objects here? So M is the Veil-Delin representation. LM is the representation of GL2 of QP that it is attached to it by the classical Langlands correspondence. And GL of M is the representation of the G, so the unit in the quaternion algebra, that is attached to it by the Jacquet-Langlands correspondence. So, I mean, the upshot is that this group here knows about both the local Langlands correspondence and the Jacquet-Langlands correspondence. So that's a quite beautiful result. It's difficult to imagine of a better answer to the question of how to get a geometric representation, construction of the correspondence. So here I said that in fact I am lying a little bit, but forget about it. This is almost true. And yeah, so the important thing is that here I claim that I do everything for GL2 of QP, but actually this was done for GLN of F, for F any extension of QP. But this is work of many people, and so mainly by Harris, Taylor, Faltings, and Fark. So Harris, Taylor, so you have two towers. You have this Rietveld tower, you have the Lubin-Tait tower. So Harris, Taylor, they work on the Lubin-Tait tower. Faltings says that the two towers at infinity are the same, and so you can go down on the other side. Okay, so that's a lot of work. Let's say it's classical. And so the obvious idea is, well, you want to replace L by P. Anybody would have this idea, I think. Okay, but so why doesn't it work so easily? It's because it looks a little bit scary, because if you take the simplest space, you take the open unit ball one-dimensional over CP, and you look at the L adic cohomology for L not P, then you get 0, which is reasonable because unit ball has a cohomology which should be 0. But if you take the P adic pro-étal cohomology, you don't get 0 at all. You get the differential form on Y. And so this differential form, it's a huge space, topological space. And what is worse is that it is a CP vector space. So if you look at the Galois representations that are going to appear in this space, then almost anything is going to appear. So that doesn't look very promising. Okay, so but yeah, so but so still we were a little bit. I mean, we thought that maybe something was possible because there is a theorem of Drinfeld, who instead of computing the pro-étal cohomology of the Drinfeld of per half plane, he computed the étal cohomology for any L. And then he got a reasonable answer. There was only one problem, is that the result is correct, but the proof of Drinfeld is not correct, but the result is correct. Anyway, so we didn't know that the proof was not correct, and we wrote another proof, but it looked that maybe the statement, I mean, maybe one could actually work with this kind of space in the end. And and also the result of Greenfeld was a little bit misleading because at level 0, the cohomology is very simple, but as soon as you go up in the tower, then it becomes very complicated. So anyway, so let me state our main result. So just define this space by two abbreviated notations. So you just take the étale cohomology of the nth level and with take twist 1. So you just twist the Galois representation by 1. Otherwise, you have to twist all the Galois representations that appear. It's a mess. And now, so I mean, it's not a very intelligent terminology, but you are going to say that a Galois representation is okay if it is two-dimensional. It's DORAM, Hochstetweit 0 and 1, and the DPST is irreducible. So if you forget about the last condition, basically the representation that we are considering are the ones that can appear in the étale cohomology of modular curves. And if you add the last condition, it means that you need to have p square in the level of the modular curves if you want to see them appear. Okay, so in that case, there are two representations that you can attach to it. You have the representation of the GL2 of QP that is attached by the classical Langlands correspondence, which in this case is supercuspidal. And you also have the things that comes from the Jacquet-Langlands correspondence, which is a representation of G-Chech, which is finite dimensional and irreducible. And so our statement is that if you take any representation of GL2 of QP, which is irreducible of dimension at least 2, then you can compute its multiplicity inside this big space here. And what you get is this multiplicity is given by this p-adic local Langlands correspondence that I defined in the beginning, tensored with also as a representation of G-Chech, this Jacquet-Langlands correspondence. So this is true if V is okay, and otherwise you only get 0, okay? And so one way to summarize the result is that this big module here contains exactly the Galois representation that you would like to see, and with the multiplicity that you would like to see also. So that's basically what the statement of the theorem says. And then there is the same statement, but looking at multiplicities of representation of GL2 of QP. So again, you say that representation of GL2 of QP is okay if it is of the shape pi of V with V okay, or you have to add some easy case where you have a twist of the Steinbeck representation by a character. But basically, pi is okay if it is pi of V with V okay, okay? And the statement is basically very similar. It says that if pi is reducible, and if you look at the multiplicity of the representation, the dual of the representation inside the big module that I defined before, this is the typo. It should be V of pi. So you get the Galois representation that you want, tensor with the Jacquet-Langlands of the smooth part of the representation, and 0 if it is not okay. So if we summarize, inside this big module here, you only see representation that basically should come from the étale cohomology of modular curves, and the multiplicity are exactly the ones that you would like for a correspondence. And I should mention that both results were generalized recently by Arno van Hecke. So you can replace the Hochstetweit 0 and 1 And of course, you should replace the constant coefficients in étale cohomology by a local system. Okay. And so now, as I said, Emerton proved his local global compatibility. But what he did more. He actually described completely the completed cohomology in terms of this correspondence. So we want to do the same with the module with the étale cohomology. But if you extend the scalar to CP, then it seems that you get a module which is much too big, and there is no way to understand its complete structure. So what we do something a little bit. I mean, we introduce a subspace which is much smaller, in fact. So what we do, we look at classes that come from a finite extension of QP mod P to the K. So we reduce mod P to the K, and we look at the classes that come from a finite extension, okay? Then we take the inductive limit over all these finite extension, and then we complete. So we take the projective limit over P over K, and then we invert, okay? So when we introduced this submodule, we decided that it was clearly dense into the previous one. And then after some thinking, we decided that it was not even clear that it was non-zero. But so we still don't know how big it is compared to the previous one. Okay, so but still, that's L is fixed. The only L is my fixed field of coefficients. I mean, I could also take the inductive limit over L, but it doesn't make much difference. And so the theorem is the following. So it's a complete description of this module in terms of the correspondence. And basically it tells you that inside the correspondence, you are going outside this big module, you only see what comes from this p-adic local Langlands correspondence and nothing else, okay? So what are these, all these symbols? So here, the M is going to run through all irreducible two-dimensional representation of the Weil group. And I put quotation marks because you also have characters that show up in level 0. And so, but basically this is correct. And B runs through the blocks of representation of mod B, representation of GL2 of QP. So if you have an M, then there is a representation of GH that will be naturally attached to it, which is finite dimensional, okay? And so now what is this ring? This ring RBM. So it's a ring of universal deformation of the thing that corresponds to B. So I told you that there was a correspondence between blocks of representation of GL2 of QP and semi-simple Galois representation of dimension 2. So this is the ring of universal deformation of this mod P representation, which are OK, meaning which they are Hodge state. Sorry, they are Durham, Hodge state weight 0 and 1. And the DPST is exactly the M that we fixed. This rho MP is the associated Galois representation into GL2 of this module. And this pi rho MB is what comes from the p-adic local Langlands correspondence. So I told you it was functorial. So so because it is functorial, there is a way to attach to any family of Galois representation, actually a representation of GL2 of QP. There. And so, well, so this ring RBM is actually very simple. Why? Because, as I told you, the RAM representation, they are classified by their DPST. So here DPST is fixed. So once you fix the DPST, everything is classified by some filtration. So, but we are in dimension 2. So a filtration is basically just given by a line. Okay, and so so there is a theorem we proved with Fontaine that gives you exactly how you can recover the Galois representation attached to the data. So if you have the M is fixed, you fix a line, you define a Galois representation by this formula. So Bicris is one of these Fontaine rings. And so the theorem is that all the OK representations are of this shape for a unique couple. And so this RMB is function which depends only on the line. Okay, so this means that it is some analytic function on some open subset of P1 of M de RAM. P1 of M de RAM is just P1. And so, in fact, what you get is that this RBM is actually a product of PIDs. So it's a very nice ring. Okay, so let me tell you some things about the proofs. So, as I say, we are going to try to understand the étale cohomology, but étale cohomology is very difficult to attack because the only way we know to deal with étale cohomology is to use integral p-adic theory, and this is quite delicate. But here we are lucky because we can recover the étale cohomology from the pro-étale cohomology by looking at the elements which have an orbit which is under the action of GL2 of QP, which is bounded. And pro-étale cohomology uses the study of pro-étale cohomology uses rational p-adic theory, and which is much easier, still not so easy. So our tower is a tower of curves. So we have a general statement for a curve. So we start from a curve over CP, and we define O, omega-1, and so on by just removing the name of the curve. Otherwise, it does not fit into Beamer. And so the theorem is the following. So assume you have a Stein curve. So a Stein curve basically means a curve without boundary. And in practice, it means that it is a curve which is an increasing union of affinoids. Okay. Then you have a functorial diagram of Frechet spaces, which describes the pro-étale cohomology. So the pro-étale cohomology is an extension of the function modulo the constant by this space. So this is the Yodo-Kato cohomology, which is a lattice inside the RAM cohomology. So the second line is just the RAM complex, okay? And so what? And so this H1 Yodo-Kato here. So it is a QP-NR vector space, QP-NR, with Frobenius and a monodromy operator. And you also have a Yodo-Kato isomorphism with the RAM cohomology. So if you extend the scalar to CP, you recover the RAM cohomology. So as I said, everything is Frechet. So here, this is a projective limit of finite dimensional vector spaces, but still you need to complete the tensor product. So it's a huge space, really huge. Yeah, and one thing which is good is that actually this Yodo-Kato cohomology. So because there is a phi and an n, and also some residual action of a Galois, then it's naturally a Veil-Dolin representation, and it's the same Veil-Dolin representation as the étale cohomology over QL for L not P. And we are lucky because people actually computed this Galois, this representation as a representation of GL2 of QP. So we can use this. So of course, when I write isomorphic, then everybody should scream, because here you have a vector space over QP and R, and here you have a vector space over QL, but everybody will know what I mean by isomorphic. Yeah? And so to...
Excuse me. Yeah.
We are not over time. I still have at least 3 minutes.
Yeah, 45.
Yes, but as I pointed out, I did not start at 45 because he stopped at 45. So I'm going to finish this slide and I stop, okay? Yeah, so where was I? So you want to factor out the G-change action, which is not very interesting. So you do this by just fixing M, and then you factor out the representation of G-change that corresponds to M. And so you get a commutative diagram like this. So the upper part is just a direct consequence of the previous theorem, plus the computation of the L-adic cohomology that I mentioned before. And the bottom part comes from a result of Dospinescu Lebras, who computed the Durham complex of this tower of Drinfeld, this Drinfeld tower. So it was a conjecture of Breuer-Strauss that they proved. And so, as I said, and so if you take one of these representation VML and you look at the multiplicities of this representation in the various spaces, so you need to compute the multiplicity for CP and decreased tensor M, because this is what happened appeared in the previous slides. And so what you prove is that it is one-dimensional. And so what you get actually is that this space is, I mean, you recover this. So the multiplicity of this Galois representation is this. And now, so you get the multiplicity in the pro-étale. And now you take the bounded vectors, G bounded vectors, and you get finally the result you wanted using the result I mentioned at the beginning, that this p-adic local Langlands correspondence tells you how to recover representation of the L2 of QP from its locally analytic vectors. Okay, so that's all I want to say about the proof. And then, so we wrote 6 papers on this kind of topics, and so they are here. And since I don't have time to make any comments, I'm not going to make any comments.
Yes. Okay, are there any questions for Professor Colmez?
Mod P coefficients. Yeah, so to prove the theorem that describes completely the cohomology, then you actually need to work mod P to the n directly, and you need to use integral p-adic homologies, integral p-adic Hodge theory, which I told you was much more difficult. And yes, so.
Any more questions?
Wanted to know whether on the top of the Drinfeld tower,
Yes.
up to p-adic completion, has some perfectory properties, and whether it is used in the proof.
No. So here we don't complete at the so because if we completed, we would get a much bigger spaces. So here we really look at the projective system of curves, which means that all the cohomology are just the inductive limits. Okay, but it is true that if we looked at the cohomology of the completion, then there is a hope, because here we have some restriction on the representation that can appear. They have to be okay in my sense. And if you look at the cohomology of the completion, then you should see everything. You should see the entire, but the problem is that you have this representation of GH, this GL of M, that gets very complicated when you go to when you complete, and it's not completely clear what the statement should be. So.
If there are more questions, let's thank the speaker again.